Hello ladies and gentlemen, let's take a look at question 7. Now here's a block. It has weight 50 newtons and a volume of about 2 times 10 to the minus 3 cubic meters. It's suspended by a spring balance above a beaker of water. The weighing scale is calibrated such that right now the weighing scale is reading 0. So when the block is fully immersed into the beaker of water, what is the reading on the spring scale? And what is the reading on the weighing scale? So that's what we need to find out. Now, first of all, let's take a look at some concept. The concepts for this question is that a spring scale reads tension and a weighing scale reads normal force. So we need to find out first what's the tension on the block. So let's take a look at the block. Now, this is the block in the water. The block in the water will have a weight acting on it, mg, which is 50 newtons. And then it's going to have an upthrust acting on it, U, as well as a tension, T. Now the weight and the upthrust and the tension are going to add up to be the same value. So basically the tension plus the upthrust will be equals to the weight. So we need to know how much is the upthrust. So upthrust will be V rho G. The volume of the block is 2 times 10 to the minus 3. The density of the water is 1000 and G is 9.81. So the upthrust is going to be 19.62. So that means T plus 19.62 equals to 50. Well, that tells us that tension is equals to 30 newtons. So the tension in the wire is 30 newtons, which means that this is 30 newtons. 30 newtons. Okay, so let's take a look at the value of the forces on the block. Now the weight of the block is 50 newtons. The tension on the block is 30 newtons. And the upthrust on the block is kind of like 20 newtons. But where does upthrust come from? Now upthrust comes from the water. So it's upthrust, okay, it's the force by the water on the block. Okay, force by water on the block. Now here's the water but without the block, so I'm going to draw the water without the block. Okay, so this is the water with the block as an empty hole inside here. Now when a water pushes up on the block by 20 newtons, the block will push down on the water by the same amount because of Newton's third law. This will be the force by the block on the water. So that means that when the block is inserted into the water supports the block 20 newtons and the block pushes the water down 20 newtons. Hence the block exerts a force on the water downwards. So the weighing scale reading will be increased by 20 newtons due to the force that the block exerts on the water, and the weighing scale reading will be 20. That's the end of question 7. Let's take a look at question 8. Now, in question 8, the main concept for this question is that the choice of the pivot for moments questions is very strategic. So if you choose the pivot correctly, your answer will be very easy. But if you choose the pivot wrongly, then your answer will be very difficult. So a heavy uniform beam of length L is supported by 2 cords. Because the question tells us that it's heavy, so we have to draw the weight of the rod, and the weight of the rod will be in the middle of the rod. Now determine the ratio T1 and T2 of the tensions in the cords. There are 3 places that we can choose to take the moments. We can choose to take it at A, we can choose to take the moments at B, or we can choose to take the moments at C. Now, because they want the ratio T1 over T2, the best place to choose the moment will be at B. So if we take moments about the center of the mass, the sum of clockwise moments will be the sum of anti-clockwise moments. So let's take a look at this rod over here, and we're going to take moments about this center of mass. Then the clockwise moment is going to be T1 multiplied by 50% of the length, 0.5 L. And the anti-clockwise moment, T2, will be T2 multiplied by 0.2L over here. And these are going to be equal. So the sum of the clockwise moments, remember the moment equation is given by the moment is equals to T1 times the distance times the sine of the angle between the force and the distance. So since the sine of the angle is 90 degrees, that will be T1 times 0.5 L times sine 90 degrees, which then we can put this inside here. Okay, we'll do T2 the same way, and we can find T1 over T2 is 0.2 over 0.5. Okay, that will be 0.4. So this is question 8. Remember, the choice of the pivot is strategic. Now let's take a look at question 9. Two cords are used to hang a lamp of weight 20 newtons as shown. What is the tension in the left cord and the tension in the right cord? Now, so T1 is pulling in this direction and T2 is pulling in this direction. And then of course there will be a weight mg pulling in this direction. Okay, so let's draw the forces acting at this point. So over here we have 20 newtons. This point meaning this dot over here. Okay, now 20 newtons, and then we have T1 in this direction, which is at 30 degrees. Because of that, we can then resolve T1 into two forces. Here will be T1 sine 30, and this will be T1 cosine 30. Now likewise, we can also resolve T2 in two directions. This will be T2 sine 60, and this will be T2 cosine 60. Now, it then tells us that we can do two equations. The vertical equation tells us that T1 sine 30 plus T2 sine 60 is equals to 20. And, we can then write, sine 30 in terms of a number, which is 0.5 T1 plus 0.866 T2 is equals to 20. Now, likewise, we can do the same for the other side. T1 cosine 30 is equals to T2 cosine 60. This will be in a horizontal direction. So T1 cos 30 minus T2 cos 60 is equals to 0. Now, once again, you can write the numbers, for this equation, which I've done on the working on the left, and plug it into a calculator. Once you do that, you can solve for T1 and T2. So this is the end of question 9. Okay, let's take a look at question 10. Now, the concept for question 10 is that tension acts in both directions along the string, and tension is constant in the string. Now, this problem can be solved more easily by breaking it up into two parts first. So let's take a look at the block B. So here's the block B. It's acted on by two forces. The weight is 12 newtons. So that means in order for block B to stay stationary, that means the string is also pulling up by 12 newtons. So that means the tension T is equals to 12 newtons. Now remember that tension acts along the string as well. This means that for block A, it's being pulled up with the same tension of 12 newtons, because tension acts in both directions along the string and tension is constant in the string. So if this is 12 newtons tension, then this one is also 12 newtons tension. Okay, of course, this is only true for JC, and when you go to university, you will learn something else. But never mind. Okay, now, so what else is acting on block A? Now, because block A is on a slope, we shall put in the slope equations, for the weight. Now, only sum of the weight acts down slope, and the sum of the weight will be sine 30 degrees. Okay, so 20 sine 30 is the weight component that acts down slope. But take a look at this. 20 sine 30, if you work it out, is only 10 newtons. So the tension is 12 newtons and the weight is 10 newtons. Doesn't that look unbalanced? So how does the block stay still, stationary on the slope? That must mean that there is also a friction force of 2 newtons that is holding the block along the slope. Does it make sense? Okay, so let me just repeat again. Look at block B first. 12 newtons weight is balanced by 12 newtons tension. The 12 newtons tension is carried along the string and acts on block A. So the tension pulling block A up the slope is 12. The weight component pulling block A down the slope is only 10. For the block to stay stationary, the friction must be 2. And that's question 10. Now let's take a look at question 11. Hungry bear weighing 700 newtons walks out on a beam to retrieve some goodies. The beam is uniform, weighs 200 newtons and 6 meters long. The goodies weigh 80 newtons. Draw all the forces acting on the beam. So let's draw the bear. Okay, so this bear pretty heavy, 700 newtons. And then the beam is also pretty heavy, halfway down the beam, which is about 200 newtons. And then the goodies weighs 80 newtons, so this is 80 newtons. And last but not least, the tension along the wire, we call it T, that would be the tension. So if the wire can withstand a maximum tension of 900 newtons, calculate the maximum distance the bear can walk before the wire breaks. Now this is a straightforward moments question, so we shall take the moments about this point. Taking moments about the hinge, the sum of the clockwise moments will be equal to the sum of anti-clockwise moments. So what is the moment of this bear? The moment of the bear will be 700 multiplied by x. What about the moment of the center of mass of the rod? The center of mass of the rod will be 200 multiplied by 3, which is the distance, because the rod is 6 meters long. So the center of mass must be at the 3 meter mark. Now the goodies will have a moment of 80 times 6. Okay, and the tension will have an anti-clockwise moment of tension times 6 times sine 60, because this is the formula for the moments. Force times distance multiplied by the sine of the angle between the force and the distance. So if we equate all this, this plus this plus this will be equals to that. So putting it all together, 700x plus 20 times 3 plus 80 times 6 is the maximum value that you can have is 900. So we put 900 times 6 times sine 60, and you get x is 5.1 meters. And that is question 10. 11. Let's take a look at question 12. One end of a uniform beam of this length and mass is pivoted to a wall, and the other end is attached to an inextensible rope shown. Use the principle of moments to calculate the tension in the rope. Now the first thing we need to do is to draw all the forces acting on the beam. The first force acting on the beam will be the weight, 50 times 9.81. When we draw the forces, we also need to draw the angles between the forces and the beam. Now let's take a look at this. This is an alternate angle, so this angle will definitely be 60 degrees. There's another force at the end of the beam. That force is the tension T. And the tension T, the angle that it makes with the beam, will be 180 minus 60 minus 55, which means that this angle is 65 degrees. Now finally, there is one last force acting on the beam, which is the reaction force from the hinge. Now, using the idea of concurrent forces, all three forces must pass through a common point. So this is the reaction force. It will pass through the common point over here, the concurrent point at the top. So now that we've got all our three forces, let's think about where to take the moments. Remember, the selection of the pivot is strategic. Now Because we don't know what R is and we don't know what angle it makes, we're going to choose this as the pivot so that we can neglect the moments from R. So we choose taking the moments about the hinge. The sum of clockwise moments will be equal to sum of anti-clockwise moments. Okay, so how do we find the clockwise moment? The clockwise moment is found using this formula. The moment is equals to force times the distance multiplied by the sine of the angle between the force and the distance. So the force here is the weight. The distance to the center of the beam is 2.5 divided by 2 because the whole beam is 2.5 meters. So this will be 2.5 divided by 2. And the angle will be sine 60. So over here we can see that we have the clockwise moment, force times distance times sine of angle. And then the other side, the anti-clockwise moment is also force times distance times the sine of the angle between the force and the distance. So we get tension is 234 degrees. Newtons. Okay. Now next, let's calculate the force at the hinge. In order to calculate the force at the hinge, we will need to actually, draw all the forces acting on the beam, okay, as follows. Now over here, this is 50 multiplied by 9.81, which is the weight. Now over here, we have the tension acting at 65 degrees. Okay, so the problem with this tension is that we are going to need to kind of like resolve it in a horizontal and a vertical direction. Okay, so how do we resolve the tension in a horizontal or vertical direction? Well, one clue is on the left side of the tension. You notice that this is 55 degrees. So if we use this triangle over here, with a vertical wall, the tension makes this kind of angle. So this is the tension, and this is 55 degrees. So that means that the tension acts in two directions. The tension acts upwards and the tension acts to the left. And this will be equals to T sine 55 degrees. And this over here is Ty, right? Ty will be T cosine 55 degrees. Now at this point, if you want to take some time to examine how the y and x directions of the tension was resolved, you can pause the video and try for yourself, okay, whether you can get the same results that I did. Okay, now likewise, there will be a value of R over here. Now this reaction force R can be split up into two components, the y-axis and the x-axis component, vertical and horizontal components. So we decide to draw it like that, R and a theta over here. Okay, and then we'll find the values of R later. Okay, so now let us convert this beam into a free body diagram. It will have these components of force. 50 times 9.81 acting downwards. Okay, then acting outwards for the tension, we have T cos 55. Then acting to the right, we have T sine, acting to the left, we have T sine 55. So let me just draw the arrows again because I kind of messed it up. So we'll draw it on the point over here. Alright, so this is T cos 55 and T sine 55. I'll move this to the words over here. Okay, and then for the reaction force, we will have two components. We'll have Ry and then we'll have Rx. So now we can write a couple of equations. Let's try vertically first. The vertical forces are Ry, T cos 55, and 50 times 9.81. And they are equal to each other. Sorry if the diagram was not very visible just now. Okay, so the vertical forces will be Ry, t cos 55 and 50 times 9.81. So Ry plus t cos 55 will be equal to 50 times 9.81. So we can actually do the math, and we get Ry is 356 newtons. Now, what about the horizontal forces? Rx is equals to t sine 55. So Rx will be t sine 55, and that will be 192 newtons. So now that we got Rx and Ry, it's possible for us to find the combined value of R and theta using Pythagoras theorem and trigonometry. So the reaction force will be 404 newtons, 28 degrees clockwise from the vertical as shown in the diagram. And that will be question 12. Now question 13 is very much like question 12, right? So let's take a look at question 13. Uniform ladder of weight 50 newtons. So let's draw the weight down. 50 newtons. And when we draw the weight, we should also draw the angle over here, which is 40 degrees. Are resting on a rough floor and leaning on a smooth wall. Now, because the wall is smooth, there will only be a normal force. There will not be a frictional force. Okay, so this is the normal force. Now, we also are able to write the angle between the normal force and the beam, because it's an alternate angle, is 50 degrees. The contact forces exerted on the ladder where the wall and the floor are R wall and R floor respectively. Now, because this is a rough floor, so there will be friction. And we know that because of the concurrent point, this reaction force from the floor must pass through this point. So we call it R floor. Let me just write that a little bit clearer. R floor over here and R wall over here. So on the above diagram, draw the forces R wall and R floor is drawn as shown. Now for R floor, let's just make this angle theta or something. Okay. No, we'll make the other angle theta. So never mind. Okay. So let's first find R wall. Now the correct choice of the pivot is very important. So we're going to choose this point as the pivot for our moments. Taking moments about the contact with the floor. Now, if you take moments about the contact with the floor, there are two forces that are trying to turn the rod. One of them is your 50 newtons at 40 degrees, and the other one is your R wall at 50 degrees over here. Okay, so sum of clockwise moments is equal to the sum of anti-clockwise moments. The clockwise moment will be 50 multiplied by half the length multiplied by sine of angle between the force and the length. The reaction moment from the wall will be R wall multiplied by length multiplied by sine 50. So using this, we can find that R wall is 21 newtons. That's our first answer. Now, next, we're going to take a look at the reaction force from the floor, and then we'll draw the force, the free body diagram of the beam. Okay, so here's the beam compressed to a single point. The beam is acted on by R wall, which we know from above is 21 newtons. It's also acted on by our weight, which we know is 50 newtons. And so it must be acted on by the reaction force from the floor, the friction force, as well as the normal force. Normal force, of course, will be 50 newtons, and friction force, of course, will be 21 newtons. Together combined, they will form the reaction force with the floor. So we draw this over here. Okay. Now, in order to find the reaction force from the floor, it's a simple Pythagoras theorem. 50 squared plus 21 squared, and 54 newtons. And the angle will be the arctan of 21 and 50, 23 degrees. So the reaction force from the floor is 54 newtons, 23 degrees clockwise from the vertical. Now, let's take a look at part D. The maximum value of the friction force is 45 newtons. Determine the smallest angle between the ladder and the floor so that the ladder can lean before it starts to slip. Now, if the maximum friction force on the rough floor is 45 newtons, this is 45 newtons, and we know that the weight is 50 nutons, so this is 50 newtons. And we know that the normal force on the floor must also be 50 newtons. And we know that the smooth wall must therefore be 45 newtons. Okay? So these are all the forces acting on the rod. Now, the thing now is to find out what angle can it lean. Okay, so what angle can it lean? So let's take this point as the pivot over here. Let's take this point as the pivot. And assuming this angle is theta, then this will be the weight, 50 newtons, and this angle will be 90 minus theta. 90 minus theta. Okay. And down here will be 45 newtons because we know that's the maximum force from the normal, force from the smooth wall, because the friction is also 45 newtons, and the angle here is theta. So now we can do the equation as follows. 50 multiplied by half L multiplied by sine 90 minus theta is equals to 45 times L times sine theta. Now, you can either solve this using a calculator's equation mode, or you can tell that sine 90 minus theta is cosine theta. So actually what this means is that 25 cos theta is equals to 45 sine theta. And we can bring the cos theta underneath the sine theta to like so. And we can bring the 25 and 45 over here, which means that tangent theta is equals to 25 over 45. And you can solve for theta. Theta is equals to 29 degrees. So that would be the answer to question 13. Now let's take a look at question 14. A car of mass 1000 kilograms with engine off rolls down the slope at a constant speed Vt. The resistive force on the car consists of a frictional force of 1000 newtons and air resistance, which is given by 40 V squared. What is the terminal velocity? Well, let's take a look at the forces acting on the car. Okay. Now, the main forces acting on the car which we're interested in is the component of the weight downslope. As you know by now, the component of the weight downslope will be sum of the weight, meaning sine 20 degrees. Then after that, we have a friction force, which is 1000 newtons plus 40 V squared. Okay. So this is the weight downslope, and this is the resistive force. We have a friction, and we have air resistance. Right. So when the car reaches a maximum speed, we can tell that these two forces pulling down the slope and the friction and air resistance must be equal. So since the car is at equilibrium, the component of weight downslope is the sum of resistive forces acting upslope. So 1000 times 9.81 times sine 20 equals to 1000 plus 40 V squared. So the velocity will be 7.67. Actually, I should write Vt, right? Is equals to 7.67 meters per second. You can leave it to 2 sig fig as well, because the data is 2 significant figures. And that's the end of the tutorial.